This is a talk about information flow, by which we mean the dependencies between the sources or inputs and the sinks or output observations in a system. In this picture, we are modelling what we call, for the sake of this talk, a conjunctive dependency. W depends on both Y and Z. And typically when we talk about dependency, we usually mean may depend. These are upper bounds on dependency. And this is typically how we use dependencies to reason about security and privacy in information flow. Now, there are many varieties of information flow, stated at various degrees of granularity. For example, fine-grained information flow may describe what parts of a data a given output may depend on. There are also various forms of conditional dependency. For example, a popular security one might be where the security labels themselves are dynamic, and so the dependency properties may depend on dynamic checks on those labels. Now, there are various semantic models that allow us to model these kinds of information flow, and at their core there is a common core which has been dubbed the Lattice of Information by Landauer and Redmond, and this is a lattice formed by equivalence relations. In this talk we discuss what you might say is a missing abstraction, something which is not easy to express directly using the lattice of information. And that is something we're calling disjunctive information flow, illustrated in this picture, where W depends on Y or Z, but not both of them, at least not at the same time. To understand this in more concrete code terms, it may be useful to look at a basic program which illustrates this. And this is the smallest example which does that, a conditional which either assigns Y to W or Z. We want to be able to say that W depends on X and Y or X and Z. But the problem tackled in this work is that we don't really know how to express this or what it means semantically. Before we get into that, what is this kind of information flow property good for? Why would we be interested in it? Well, a good example that illustrates the need for disjunctive information flow is when we want to give an information flow interpretation for the so-called Chinese wall security policies. We'll refer to these as ethical wall policies, introduced by Brewer and Nash in '89. So these policies, somewhat different from the military message passing models, deal with commercial systems and the notion of conflict of interest. So imagine a consultant who can work in a number of different domains, for example, banking or telecom or automotive. Within each of these domains, however, they can't work for multiple clients. That's because they may learn information from one which will cause a conflict of interest with another. So, for example, if we have these conflict of interest classes of banking and so on, and we have a number of possible clients in each of those groups, then a consultant may only work for one of them. So this is the ethical wall policy. There's no constraint over which one the consultant works for, or indeed on the conditions under which they work for them, just that they may only work for at most one in each group. We argue that this is a natural notion of disjunction in information flow. So the contributions of our work are to develop a semantic model for disjunctive information flow, which directly generalizes the lattice of information. And we will show in the paper that we can model disjunctive policies like the ethical wall policies in a direct and satisfactory way. We also show that our model satisfies a number of useful properties for reasoning about programs and systems, in particular that it enjoys certain compositionality properties. So in order to dig into a little bit of detail, let me remind you a bit about the so-called lattice of information. The terminology lattice of information comes from a paper by Landauer and Redmond from CSF in '93. So the idea is to use equivalence relations to model information, and we're going to visualize these and work with them in the form of partitions of a data set, an equivalent way of representing an equivalence relation. So let's assume, for the sake of a concrete example, that we have a data domain with 4 values in it. And we assume that the observer always knows the data domain itself. So the idea that we have no knowledge about this data point in this domain is represented by no partitions of this data, or alternatively, one big equivalence class. Now, if we were to observe the output of dividing a value by 2, then we would learn the parity, and that's represented by partitioning this data set into two equivalence classes with the odd numbers and the even numbers respectively. If alternatively we observe the output of the test whether the value is equal to 0, then this is what we learn about the data item, that it's either in this equivalence class or it's in this one. And if we learn both of those facts by observing both of these outcomes, then what we learn is a combination of these two. And that combination, or conjunctive combination as we'll call it in this work, can be represented in the lattice of information by a least upper bound operator, which refines both of these partitions to give us this one here. So here's a visualization of a sublattice of the lattice of information over this particular domain of 4 values, with the top element representing full knowledge of the value, and the bottom element representing no knowledge of the value. And these are the points we just saw in the example. Now, that's a model of information. What about information flow? Well, information flow is modeled by using equivalence relations to model the way the observer observes the data and the way and what can be possibly learned from those observations about the inputs. So here we're modeling computation as a function. And the right-hand equivalence relation is modeling what can be observed, and the left-hand modeling what can be learned about the input. And so in particular, if we take any two values in the same equivalence class, they will get mapped to equivalent things on the right-hand side. And many of you will be familiar with this concept from notions of non-interference. Okay, so what about disjunctive policies? Well, the lattice of information can express a specific disjunction by using a conditional form of information flow. So we can say, for example, that our consultant here working in the automotive domain will end up working with Volkswagen if they speak German, but Volvo otherwise. So this kind of information flow property, a very specific one, a specific disjunction, can be expressed in the lattice of information. What we can't do is to directly express the situation where we simply don't know or don't care what the conditions are under which this task is assigned. So it's important to abstract this because such conditions may be complex, unknown statically, but also completely irrelevant. We're simply not interested in them, as in the example of an ethical wall. So the lattice of information then, in summary, gives us a way of modeling knowledge using equivalence relations, which includes a notion of conjunction of information as the lattice least upper bound, but does not have a direct model for disjunction of information. Our work generalizes this by looking at a quantale. A quantale is a structure which is like a lattice but has an additional operation and additional constraints on how that operation interacts with least upper bound. So our work generalizes the lattice of information by lifting from equivalence relations to sets of equivalence relations. The notion of conjunction of information in our quantale of information is modeled not by the least upper bound operation of the quantale, but by the tensor operation, this other additional operator. And it's a pointwise operation in the way described in this picture. The key here is that we can represent disjunction of information, and roughly speaking, the idea here is that we're going to use set union to represent the disjunctive combination of information. Now, this seems very simple, and in fact it's too simple to be true. When we use union to represent disjunctive combination of information, we actually don't get enough elements in our sets to do the job that we intend. The secret sauce here is that we need to use not just any old sets, but sets which are closed under a particular operation. This operation involves taking the members of these sets, the equivalence relations in these sets, and closing them under a special mixing operation which allows us to mix and match the various equivalence classes. This operation is called tiling, and I'll give an intuition of what tiling is. So tiling closure of a set of equivalence relations. The idea here is that we are thinking of equivalence relations in terms of their equivalence classes. And we can think of equivalence classes as possible observations that are made about the equivalence relations. Tiling closure of a set of equivalence relations or partitions corresponds to all the relations that can be built by mixing together the equivalence classes, the possible observations that they represent. So visualizing this, suppose we have a set containing these two equivalence relations, represented as partitions. Then we can build some new relations from these by mixing and matching their equivalence classes. We can build this one, And we can also build this one. So the tiling closure of any set of relations containing P and Q will also contain these two multicolored relations. So our conclusion, we in this paper introduce a quantale of information, a strict generalization of the lattice of information. And in the paper we show how this captures in a very precise sense the essence of the ethical war policies. We also show a number of other things, including that our model satisfies nice composition properties, which hopefully paves the way for static analyses of disjunctive information flow. Thank you for your attention.